Hello everyone, this is Mr. 13 Things coming at you once again, this time following up on the concepts of what are the true and then the estimated values for some of our key numbers, the radical numbers, square root of 2, square root of 3, square root of 5, and the unit ratio. And actually, why not throw pi in there, because it's one of our most important irrational and ever-present numbers or ratios. So we're doing that around the unit circle, so we'll get back into that. This time I'm going to let you know I'm going to put it on a couple of different layers and then see how we can push perhaps some of this stuff out to some sort of a quizzing mechanism on either TED-Ed or on the Khan Academy exercise framework. So I'm going to add a layer here which you can't see. All right, so we're looking at conceptually the fact that if we can get our minds around E, I, pi, 0, 1, minus 1, the square root of 2, the square root of 3, the square root of 5, the golden ratio, a matrix, and a single vector. I'll call that A, B, C, D, and A, E, F, if you would. If we get our minds around these things, we'll be a long ways to getting deeper into the funner math earlier. This is 13 things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, forgot infinity. Okay, Mr. 13 Things, that's where the name comes from. And we've looked at the earlier video of the construction of the square root of 2 if in fact this is, keep on trying to get my circles better, if this is the unit circle, the radius equals 1, the diameter equals 2, the area equals pi, and the angle equals 2 pi, then in fact this distance there is the square root of 2. And if this is the unit circle, again, and if in fact we then divide this in half, take that line through there, this here is the square root of 3, and if in fact this still is the unit circle, and we kind of take this here, make the box, and do that edit, undo, edit, undo. If we make the box here, take our halfway point. I'll switch colors for this, see if I can do a better job of drawing out what that circle is. If we take that radius here, right, and spin it down to here, so we have that distance there. Take a line through there. This distance here is the square root of 5, and that distance there, which is the average of 1 and the square root of 5, is the golden ratio phi. Getting students to learn that you can express values, if you would. I'm going to go back to the suck the color tool. You can express the values as either a length. So for instance, this is obviously the length square root of 2, and this is the length square root of 3. And if you're doing these to scale, you have something you get in class, hopefully, or with your daughters or sons, you get something called dividers, because this is really best done as a tactile exercise. If in fact kids are not going to stick themselves with that hole, right? A divider is kind of like a compass. Divider or a slash, a compass. Not a compass in the woods, but a compass as in spin a circle. So that idea of a divider here. All right, so the concept that here you're expressing these as lengths, but when you start looking at maybe other values, for instance, the square root of 6, right, which is actually equal to the square root of 2 times the square root of 3, you could think about these as perhaps this way. The square root of 6 can be expressed as a percentage of a circle, I'm sure. Square root of 6, which is more than 2 less than 3. So it will be a portion of the circle, if you would, but it could also be expressed as this length right? Times, if you kind of take that square root of 3 length here and spin it perpendicular. Something like that. So if that's the square root of 3 and that's the square root of 2, that's the square root of 6 because you take length times width. So learning that our eye can pick things out based on comparing lengths or comparing areas is a pretty useful adventure to come upon early, because later on you're going to see it's very key to trigonometric functions, trig functions, but more importantly, hyperbolic trig. And if you don't think you have any use for hyperbolic trig, don't get on a free trip down a zip line in Costa Rica if someone gives it to you. So hyperbolic trigonometry is basically gets you to the math of catenaries. So wires that hang under their own weight. Biggest example in Wisconsin of a catenary would be a anchor chain. All right, so to get at how hyperbolic trigonometry works, you've got to get at kind of area representations of angles, and that's why, in fact, for no other reasons why you have to learn to express these key values not just as distances but also as areas. So if you think about it, this would be the square root of 6, but if you wanted to, you could also draw that unit circle, right? Draw that here, and then take this same radius and swing it out. Square root of 2 is more than 1, so that might be something like an area expressed as the square root of 2. Same thing here. This distance here might be the area expressed as the square root of 3. The area expressed as, in this case, this would be the area expressed as the square root of 5. So the concept, because this is a radius 1 here, the concept that you can express these key numbers as not just distances but also areas. And let me go ahead and erase everything out and get to, once you truly start to, or students or learners really start to kind of get the fact that, oh, numbers can mean different things, they can also then maybe get to the point of knowing that once you understand what they are, sometimes you just want some good computational numbers to get really close, some approximations. So the fact is, you would never measure the square root of 2. You might say it doesn't exist, but that wouldn't be necessarily true. The square root of 3, these are irrational numbers. They never end in terms of decimal form. So the fact is, but a good approximation for the square root of 2 is come upon this way. It's about equal to, and I'm going to do this, 1 over 1. I take the 1 plus 1, put it on the bottom, take the 2 plus 1 and put it on top 3, and I cross this out. But now I take the 3 plus 2, put it on the bottom. 5 plus 2 is 7, and I cross this out. But then I take the 7 plus 5, put it on the bottom, 12. 5 plus 12 is 17. But then I take the 17 plus 12, put it on the bottom, 29. The 12 plus 29, and you've got a pretty good approximation here. But not as good as if you take the 41 and the 29 and put it on the bottom and have 70, and then you have 99. And this one is just kind of a nice number. But you could keep going, ... This is an approximation for the square root of 2. It turns out I don't know of a good one for the square root of 3, and the square root of 5 one is kind of odd. But for phi, it turns out to be the ratio of two numbers in the Fibonacci series. Ratio of two numbers in the Fibonacci series. Lots of different people talking about that. But how do you get the Fibonacci series? It begins in 0 and 1 as your starting point, as opposed to the Lucas number. 0 and 1 together is 1. And then 1 and 1 is 2. And then 1 and 2 is 3. And then 3 and 2 is 5. And 5 and 2 is 8. And 8 and 5 is 13, and 13 and 8 is 21, and 21, and now you're at 34, and 34 and 21 is 55, and 55 and 34, 89, and then you get there, and then you're up to this interesting one, 144. Do the math, you'll see it. 144 and 89 is 233. Do the math and you'll see it. This next one, 144 and 233 is 377. Do the mathematics. I'm sorry, the arithmetic, you will see it. And then the next one is 610. And somehow for me, 610 over 377 is a good approximation of there. As you do these, right, you tie yourself to one of the key things in higher order math, that everything can usually be expressed, important numbers can be expressed as a sequence or series, an infinite series. And we won't go so far beyond there, except for the fact that then the square root of 5, it turns out, is the square root of 5 comes from this. Phi equals 1 plus the square root of 5 over 2. So the square root of 5 is 2 phi minus 1. 2 phi minus 1. And so this would be square root of 5 equals 1220 over 377 minus 1, which is 377 over 1220. And for that, you'd have to, I'll take a struggle here to actually do the, 377 over 377. I'm going to try to do the math, and then we'll check it with a calculator. So 10 minus 7 is 3. 11 minus 7 is 4. 11 minus 3 is 8. 843 over 377 is not correct. So let's take a look at our math again. 610 over 377, in fact, is phi. Phi equals 1 plus the square root of 5 over 2. It's the average of 1 and the square root of 5, as you saw from the geometry. 2 phi minus 1 equals the square root of 5. The square root of 5 is 2 times 610, which is 1220 over 377, minus 377 over, oh, this actually probably is correct. Square root of 5 is more than 2, less than 3. So let's now take out that calculator that we don't use too often here. Put it right here on the screen and see what happens if we take 843, which you'll never memorize. It's not a good idea. Actually, the square root of 5 is not the important number. It's just that's the way to get you to phi. 843 divided by 377 equals 2.236 minus, let's see, how do we get a square root? Useless calculator. Minus 5xy 0.5 equals, and that means pretty much that's a pretty good approximation. It's in the order of it, off by 6 millionths or something like that, an order of 6 millionths. So this here becomes the square root of 5. All right, so ei pi 0, 1, minus 1, the square root of 2 minus the square root of 3, square root of 5, phi. A matrix, a vector, especially how they work together, and infinity. The last one, just so we can keep on the theme and not forget on this one, is in fact, I'll do edit cut. There's lots of ways to express pi. It's a really important, probably one of the most important numbers to learn. You learn it in 5th grade, and they give you all kinds of ways to do it. A lot of people use 22/7 pi. It's close to that. But in fact, if you want to get really close to pi, you can't get it in the series so well, but you can get pi over 4, and it looks like this. 1 over 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11 plus 1/13. And you better be good. Plus, minus, plus, minus, plus, minus, plus, minus, dot, dot, dot. This will get you pi over 4. Thanks for listening.